Okay, let's move on to problem number 3. In this problem, you're being told that a 10-minute experimental run shows that 75% of liquid reactant is converted to product by a half order rate. What would be the fraction converted in a half-hour run? Okay, so the first thing you need to look out for here is the half order rate. And the half order rate basically corresponds to one of our cases, right? So now we're working on right, so we're working on number 3. So you're being told, let's write the minute, the given t equals 10 minutes, x is equal to 0.75, and n is equal to half, or let's write it as 0.5. So you're being told what would be the fraction converted in a half-hour run. So let's write this as x1 and t1. So you're being told if t2 is 30 minutes, x2 equals what? So the first thing you need to look out for is this half order business, right? And this corresponds to case number 4, right? So this half order corresponds to case number 4, right? And this is case number 4, which is rate equation nth order, right? Basically n not equal to 1, right? And the governing equation for this case is CA note, or in this case, CA note 1 minus n. Let me rewrite this. CA note 1 minus n minus, it's actually CA, sorry. Just be careful with these equations. CA1 minus n minus CA note 1 minus n is equal to n minus 1 into KT. And so this is my performance equation in this case. However, I will need to rewrite it in terms of x to be able to solve it. So recall that, these are the equations I need to know. CA is equal to CA note into 1 minus XA. So I'm going to plug the CA right here. So I'm going to get CA note 1 minus n multiplied by 1 minus XA into 1 minus n minus CA note 1 minus n is equal to n minus 1 KT. And so my functional performance equation I'm going to use will be this one, 1 minus n minus 1 is equal to n minus 1 KT. And this will be the performance equation in terms of x, right? Performance equation in terms of XA, right? So now I have my performance equation. Let's start plugging in some numbers. So I'm going to plug in the numbers for case number 1. So I have t equals 10 minutes, and x1 is equal to 0.75, and n is half. So CA note 1 minus 0.5 is basically 0.5 into 1 minus 0.75 into 1 minus n will be 0.5 minus 1 is equal to n minus 1, which is minus 0.5 multiplied by t, which is 10 minutes, multiplied by k. So now I have k and CA note, there are unknown, so I'm going to do the same thing we did in the previous problem, where I'm going to lump the constants basically. And if I do that, I can get k over square root of CA note is equal to, so this is 1 minus 0.75 is what, 0.25? 0.25 to the power 0.5 minus 1 divided by minus 0.5 into 10, right? And this should give you a number. Let's try and evaluate it right here. What's the square root of 0.25? So we get 0.5 minus 1. So this will be 1 over 10, basically, right? So this will be 1 over 10 minutes. And this is k divided by square root of CA naught. So now I'm gonna plug in the second set of parameters. So in this case, I have CA naught 0.5, 1 minus xa2, or 1 minus x2 to the power 0.5 minus 1 is equal to minus 0.5. For the second case, t is equal to 30 minutes. So in this case, I'm just going to write 30. And then k, right? We're actually solving for x. So if I move this constant right there, so I'm going to move the CA naught to the other side. So I get 1 minus xa2 to the power 0.5 minus 1 is equal to minus 0.5 into 30 into k over square root of CA naught, and k over square root of CA naught, we already have it right here. And this will be equal minus 0.5 multiplied by 30 divided by 10. And this will basically be what? Minus 1.5, right? So now I just continue solving the algebra. 1 minus xa 2 to the 0.5 is equal to minus 1.5 plus 1. So I just moved this one to the other side. This is equal to minus 0.5. I square both sides, so I get 1 minus xa2 is equal to 0.25. And basically xa2 is equal to 0.75. Okay, so algebraically, this is the answer you get. However, now you need to use your engineering senses. Does this make sense? Can xa2 be equal to 0.75? You know, if I look here, 0.75, does this make sense? So xa1 is 0.75, xa2 is 0.75. You know, so something's off here. So, you know, instinctively, first thing you do, let's check our math, see if it makes sense. We didn't do anything really strange, right? We just plugged the numbers, lumped the constants, got this, plugged this guy here, got this. So the math looks fine. So what should we do really? What you need to do in these cases, and this is a typical type of scenario where, you know, if after a long time your math is fine, but the conversion you get looks very strange, what you would need to do is we need to check the Tmax, right? So at this point, you need to check. Okay, yeah. And what is Tmax, right? Tmax is basically the maximum time possible for this reaction to happen, right? So sorry, so Tmax is basically the time when your conversion is complete, and Tmax is basically the time when conversion is complete. So let me save this guy right here. Let me let's just erase this side. Is there a bigger eraser on top? Okay, it's fine. Okay, so now I need to check Tmax, right? And let's just rewrite what Tmax is. Tmax is the time for reaction completion, i.e. XA is equal to 1. So if you recall, our performance equation was CA naught into 0.5, 1 minus XA into 0.5 minus 1 is equal to minus 0.5 KT. So if I set XA to be equal to 1, in this case, I'm going to get CA naught 0.5. 1 minus 1 is 0, right? So I get minus 1 is equal to minus 0.5 K T max. And K over CA naught to the half, if you recall, K over square root of CA naught is equal to 1 over 10. So basically, there we go. So basically, if I just do the algebra here, CA naught to the 0.5 divided by K into minus 1 divided by minus 0.5 will be equal to T max. And CA naught divided by K will be basically 10 minutes. Minus 0.5 divided by 1 is 2, is equal to T max. And T max is basically 20 minutes, right? So a reaction reaches completion after 20 minutes. Reaction reaches completion after 20 minutes. So after 30 minutes, your x2 will just be equal to 1, right? So the correct answer here is that x2 is equal to 1. The reaction will be complete, right? Because it's you're not told it's reversible, you're not told anything. So in this case, your reaction will be complete. And this is a type of thing or a type of problem where you also should get accustomed to, where, you know, because a lot of these equations are derived from transient equations, which is basically dc by dt. So when you're solving these types of differential equations, you might get mathematical numbers which are mathematically correct, but practically are not correct. So you always need to practice your engineering judgment. Take a critical look at your numbers. Do they make sense? Am I just calculating junk? What's going on? And you take it from there, okay? So this was problem number 3. So this is saved. All right, let's move on to number 4. Okay, number 4. So in number 4, you're being told in a homogeneous isothermal liquid polymerization, 20% of the monomer disappears in 34 minutes for initial monomer concentration of 0.04 and as well as for 0.8. What rate equation represents the disappearance of the monomer? Okay, so I mean, let's try to approach this problem. Let's go to the solving space here. Let me clear all my drawings and let's start writing again. So this is problem number 4, right? In a homogeneous isothermal liquid polymerization, we're being told that 20% disappears, so X is equal to 0.2 in 34 minutes. T is equal to 34 minutes for both. CA naught is equal to 0.04 and CA naught is equal to 0.8. So from these results, experimentally, you know, there's a big gap between these two concentrations. So it's obvious that conversion is independent of initial concentration, right? Which means that XA and CA naught are not dependent on each other. So basically we need to find the equation find the performance equation which reflects this. So let's look at our performance. So now we just need to look at the different cases, find the performance equation which reflects this, okay? So let's go here, let's write them one by one, right? So for case number 1, the performance equation is minus ln 1 minus xa is equal to kt. There is no CA note, right? And no CA note. So this is a contender. If you look at case number 2, you'll find out that ln m minus xa divided by m into 1 minus xa is equal to k CA note m minus 1t. CA note is right here, so x will depend on CA note. If you look at the rest of them, you'll find out that x will always depend on CA note, right? X will always be as a function of CA note, right? So from this analysis, it's obvious that this is a first order irreversible reaction. So you can basically conclude that, you know, it's a first order reaction, and the governing equation in this case is the performance equation, 1 ln 1 minus xa is equal to kt. Now I can use my experimental data to calculate k. So minus ln 1 minus 0.2 is equal to k into 34 minutes. And basically k is equal to minus ln 0.8 divided by 34, which is equal to 0.00657 minute minus 1, right? Or 1 over minute. Let me just double check this number. Yeah, that's correct. So you're being asked what rate equation represents the disappearance of the monomer. So your rate equation for a first order reaction is minus dc by dt is equal to minus RA is equal to K CA. So in this case, basically minus RA will be equal to 0.00657 minute minus 1 multiplied by CA. And this is the answer to this problem. Okay, so again, this is another type of problem you should get familiar with. You know, your exam will basically be based on your homework. So this is another type of analysis you need to get to know. Okay, sounds good. Now we're moving on to it, number 5. Okay, let's have a look at number 5 here. Number 5. Okay, so in number 5, you're being told, and after 8 minutes in a batch reactor, reactant with an initial concentration of 1 mole per liter is 80% converted. After 18 minutes, the conversion is 90%. Find the rate equation to represent this reaction. Okay, so you're given some data and you're being asked to find the rate equation. Okay, so let me save this. Let's clear and let's start. Okay, so this we're talking about problem number 5, right? So you're being told that what's the situation in this case? After 8 minutes in a batch reactor, sorry, T is equal to 8 minutes, or let's say T1, X1 is equal to 0.8, and then T2, 18 minutes, X2 is equal to 0.9. You're also given Ca naught to be equal to 1 mole per liter. You're being asked to find N. Okay. So you might be tempted to, try this by trial and error. Try to basically just test all the cases. However, the way I'm going to approach it is I'm going to use the nth order case, right, which is case number 4. So I'm going to use case number 4. Actually, let's stay with the color theme we're using here. Green. So I'm going to stick with case number 4, which is for an nth order reaction. Okay. And in this case, if you recall, the equation was Ca 1 minus N minus Ca naught 1 minus N is equal to N minus 1 KT. And because I'm given information in terms of X, so I'm gonna rewrite this in terms of X. So I'm gonna say, and I'm using A to represent my species. If you just want to write C's without any subscript, it's up to you. So I'm gonna say Ca is equal to Ca naught 1 minus Xa, and this is by definition. So I'm gonna plug this guy in the equation above it, and I'm gonna get basically Ca naught 1 minus N multiplied by 1 minus Xa into 1 minus N minus Ca naught 1 minus N is equal to N minus 1 KT. Okay. Sounds good. So what do we do now? Let's take Ca naught out. So actually, this will be my performance equation for this problem. Okay. Equation I'm using for this problem. So now let's just start solving, or let's see what we can do with this guy. Okay, so now I'm gonna take Ca naught out, and I'm gonna get this expression 1 minus Xa 1 minus N minus 1 is equal to N minus 1 KT. And if you recall, a couple of problems ago, I lumped the constants, so I'm gonna do this. I'm gonna lump the constants in this case as well. So I'm gonna get K over Ca naught 1 minus N, and this will be equal to 1 minus Xa to the 1 minus N minus 1. Sorry, let's try to clean this up. Divided by N minus 1, and I'm gonna keep the T on this side, right? So T, K divided by Ca naught to the 1 minus N is equal to 1 minus Xa 1 minus N minus 1 divided by N minus 1. Right, so I have this equation, and you can use this equation to plug the two sets of conditions and get K over Ca naught and then get N, because I basically have two unknowns, or yeah, I have two unknowns. This is my first unknown, and this is the N is my second unknown, and I have two basically sets of information given, right? Okay. Alternatively, what you could do is, or what I'm going to do is this. I'm just going to say that basically K over Ca naught to the 1 minus N is equal to 1 minus Xa to the 1 minus N minus 1 divided by T into N minus 1. And I'm going to plug the two sets of givens into this equation. So I'm going to just use the right-hand side here to solve my problem. So for the first scenario, basically I have 1 minus 0.8 to the 1 minus N minus 1, right, divided by T, which is 8 minutes, into N minus 1 is equal to 1 minus 0.9 to the 1 minus n minus 1 divided by, what is it, 18 minutes into n minus 1. And this should be enough to solve your problem. N minus 1 goes with n minus 1, assuming that n is not equal to 1, right? If this ends up being a first order reaction for some reason, then this algebraic manipulation is wrong. Anyways, so taking it, let's take it here. So 1 minus 0.8 is 0.2 to the 1 minus n minus 1 divided by 8 is equal to 0.1 to the 1 minus n minus 1 divided by 18. So I mean, if you know, I don't know if you're good with arithmetic, you can see it directly here that n is probably 2, right? But even if you boil it down more, it will be obvious to you that n is 2. So if I just cross multiply, I'm gonna get 18 into 0.2, 1 minus n minus 18 is equal to 8 into 0.1, 1 minus n minus 8. I'm gonna move this 18 to the other side, right? Basically, I'm gonna get 18 into 0.2, 1 minus n is equal to 8 into 0.1, 1 minus n plus 10. And in this case, n is equal to 2, right? The only way to do it basically is to iterate, to be honest, because unless you like want to do series to expand this side, but really you need to iterate to find n. And by iterating, you usually need to start with your usual suspects, right? 0.5, it can't be 1, so 2, 3. If it's not one of these, you can probably find the which area is it in. Is it between 2 and 3 or 0.5 and 2, and try to zone in on it. But the answer in this case is 2. Okay, so because if you do 0.2 to the minus 1, right, it's 5 multiplied by 18 will be 90, right? And then 8 multiplied by 0.1 to the power minus 1, it's 80. Plus 10, that's 90, right? So in this case, oops, n is equal to 2, right? Just be careful for these types of problems. So you might get a problem like this on the test. What I'm looking for is your ability to recognize that you need to use case number 4, and your ability to basically just lump the constants, and your mathematical analysis ability to get to this point, right? Once you get to this point, you just need to recognize that this is an iterative problem to find n. You could probably use Excel to do it very easily if you want, but you know, use whatever tool you want. Obviously, you know, doing it by hand might not be the fastest way to do it. Okay, sounds good. So this is problem number 5. Good, making some progress here. Let's move on to 6, right? Okay, let's have a look at number 6 quickly. New share. Number 6. Okay, in problem number 6, you're being told that first order reversible liquid reaction takes place in a batch reactor, and after 8 minutes, conversion of A is 33.3%, while equilibrium conversion is 66.7%. You're being told to what? Find the rate equation for this reaction. Okay, so you're given an explicit case, right? First order reversible, right? A going to R. First order reversible is case number 6. So at least we know which case we need to deal with, right? So let me save this. Let me clear, and let's start writing. So this is problem number 6 in this case. Sorry. Okay, let's write our given. So you're being told it's first order reversible, which implies that this is case number 6. You're given a bunch of other information. You're given a bunch of other information. Sorry, one second. So yeah, so you're being told that this is A goes to R, CA note is 0.5 mole per liter, and CR note is equal to 0. You're also told that after 8 minutes, so T equals, or T1 equals 8 minutes, you're told that X A1 is equal to 0.33, and you're given an equilibrium conversion. So if you recall, for case number 6, when I have reversible reactions, I also have equilibrium parameters. So in this case, XAE is 0.667. So I'm going to rewrite this as 1 over 3 and rewrite this as 2 over 3 just to make the math easier, because they'll probably cancel out at some point, right? So, and you're being told to find the rate equation for this reaction. Okay. So let's have a look at the performance equation for this type of for case number 6, right? So if you have it's on slide 19. So for case number 6, which the performance equation is basically minus ln XAE minus XA minus ln XAE is equal to m plus 1 K1T and divided by m plus XAE, right? And just to recall that I have K1 and K2, and you're being asked to find the reaction rate. So before doing this, let me just simplify this into a cleaner form. So I'm going to get ln XAE minus XA divided by XAE is equal to m plus 1 K1T divided by m plus XAE. Okay, so let me just go back to the problem and remember exactly what we're looking for. What are we trying to do? Find the rate equation. Okay, so I need to find the rate equation. So let's recall the rate equation for a first order reaction as well. So in this case, the rate equation will be, let's see, it will be dCr by dt is equal to minus, and this is on your slides, dCA by dt is equal to K1 CA minus K2 CR, right? Good. So basically, I'm looking to get really to find K1 and to find K2 from this problem. Okay. So let's take it from here and let's try to solve this problem. Okay. So let me take this expression because this is our performance equation in this case. Let me just write that this is performance equation, and let's take the performance equation and start solving, right? So let's, so I have, basically I have the conditions. I have T, I have, so recall that M is CR naught divided by CA naught, and this will be 0 in this case. So this simplifies my problem. So I'm plugging in the constants given here. I have XA1 is 1 over 3, XAE is 2 over 3. So I get minus ln XAE, sorry, 2 over 3 minus 1 over 3 divided by 2 over 3 is equal to 0 plus 1 is 1, K1, T is 8 minutes, divided by 0 again, plus XAE, which is 2 over 3. And from here, I can get K1 to be, what's this guy? 2 over 3 minus 1 over 3, 1 over 3. So this is minus ln of 0.5, right? Multiplied by 2 over 3 divided by 8. So this is K1, and let me evaluate this guy, see how much ln 0.5 multiplied by 2 divided by 3 divided by 8 again. So K1 will be 0.057750. Okay, so I have K1, so how do I get K2? Let's go back to the slides and let's just have a look at what the situation is with K2. So let me go here and so I have this K1, K2, and I have this equation here where it basically tells me M plus XAE divided by 1 minus XAE is equal to K1 divided by K2. And I'm going to use this expression to get K2. Okay, so let's go back to the slides, or let's go back to the this thing, whiteboard right here. So I'm going to use this expression from the slides where it basically tells me that K1 divided by K2 is equal to M plus XAE divided by 1 minus XAE, and M is 0, and XAE is what? 2 over 3, right? So I get 2 over 3, 1 minus 2 over 3, and this is basically, what? 1 over 3 right here is basically 2, right? This is basically 2. So basically this means that K2 is equal to K1 divided by 2, 0.0577 divided by 2. And if I divide this number by 2, I get 0.02888, right? Yeah, here we go. So I have K2 now, and I have K1 as well. So my reaction rate in this, for this reaction, dCr by dt is equal to minus dCA by dt, and this is equal to K1 Ca minus K2 Cr, and this, my friends, is equal to 0.057750 Ca minus 0.02888 Cr. Okay, so just go through it slowly. Again, any issues, just come to office hours. We'll deal with it. Good. Which one was the 6? Okay, let's look at problem number 7. How many problems? This homework doesn't end, right? Not too long. Okay. Aqueous A at a concentration Ca naught. Aqueous A at a concentration Ca naught, 1 mole per liter. Let's move on to. Let me show you what I'm saying. Okay. Aqueous A at a concentration Ca naught equals 1 mole per liter is introduced into a batch reactor where it reacts away to form product R according to stoichiometry. A goes to R. The concentration of A in the reactor is monitored at various times as shown below. Okay, you're given a concentration, you're given some experimental data. For CA naught equals 500 mole per meter cubed, find the conversion of reactant after 5 hours in the batch reactor, and then you're being asked to find the rate of the reaction. Okay, so this problem is actually much easier than what it looks like. Let's go to the whiteboard. I think I saved this. Let me save it again. Let's clear everything, and let's start with this one. Problem number 7. Okay. So for problem number 7, you're just given a table of data, and you're being told that CA naught 1 mole per liter. You're being told that A goes to R, and you're given some data for T versus CA, right? You're given some information. And so what do you need to do? So for part A, you're told that CA naught is equal to 500 mole per meter cubed. Find the conversion, so find XA when T is equal to 5 hours. Okay. So, you know, this is the type of problem where you might think, what's going on here? How do you solve this, right? So just have a look at the experimental data you're given, right? You're given T, you're given CA naught, and you're being told that, you know, it's 0, 100, 200, 300, 400, and you're given that sorry, this is actually CA, not CA naught. CA is 1000, 500, 333, 250, and 200. So if your starting point is 500 moles per meter cubed, so if this is your CA naught, what's X after 5 hours? So this is, and of course, this is in minutes, and this is mole per meter cubed. So what's 5 hours from 100, right? So 100 minutes, so my T naught in this case, minutes, and if I move 5 hours, 5 hours, what? 1 hour is 60 minutes, right? So 5 by 60 is 300 by 60. Here we go, 300. So I'm looking at 400 minutes. So my C is 200, right? So I know my CA, I know my CA naught. What's X? XA is 1 minus CA divided by CA naught. 1 minus 200 divided by 500. And what's this number going to be? It's going to be 0.6, right? So this is your conversion. And just, you know, your starting point does not really have to be at T equals 0. It just depends what time you're looking at as your starting point, right? So this is a typical perspective when looking at that experimental data. Okay, also have a part B, find the rate of the reaction. Okay, so to find the rate of the reaction, let's convert this data from T versus C to T versus X, right? So let's me convert it. So I have T, and I'm gonna use X. I'm gonna write XA is equal to 1 minus CA divided by CA naught, and I'm gonna convert this data from this to that. 100, 200, 300, 400, and then assuming CA naught is 1000, right? So here in this case, I have 1 minus 500 divided by 1,000. So this is 0.5, sorry. X here is 0, X here is 0.5. X in this case will be 333 divided by 1,000. 1 minus answer will be basically 0.667. In this case will be 250 divided by 1,000. 1 minus answer, in this case it's 0.75. And then the final for t equals 400, it's 200 divided by 1,000. 1 minus answer, it will be 0.8, right? So this is the data you have, and now you just need to plot t versus xa and see if it matches any of the cases, right? So let's have a look at the cases. So case 1, ln, so I need to plot ln 1 minus xa, and if I get a straight line, then it's probably first order. So let's try to get minus ln 1 minus xa to check first order. Check case number 1 right here. So if I get these numbers, I'm gonna get minus ln of 1. So first one is 0. Ln of 0.5. Second one is 0.693. Ln of in this case I'm getting 1.09186. In this case 1.386. And for the last one, then 0.2, I'm getting 1.609. Right? So I'm getting this type of curve. So if I plot minus ln 1 minus xa versus t, you should probably use Excel for this. I guess I'll have to load Excel. So give me a second. Let me load it, and let's plot these numbers and see if it makes sense. Okay, so let me share the Excel file I have going here. Okay, and let's do it together. So just be careful when doing these things in Excel. Even though usually experimental data are given across the screen, in Excel it's always easier to, write them vertically, right? So XA will be equal to 1 minus CA divided by CA note. And I'm putting these dollar signs because I'm going to drag this equation down. And so now let's check for case 1. I'm checking the performance equation. So in this case, I'm plotting minus ln of 1 minus XA, right? Let me write case number 1. And this will be minus ln of 1 minus XA. And these are the numbers we're getting. And now we're going to test if this is actually first order or not. And the idea is you just test it versus all your performance equations, or you keep testing it until you get something reasonable against any of your performance equations, right? So this is, you get a curve right here for case number 1. Let's add a trend line and look at our metrics. R squared, okay, it's quite a high R squared, right? Is it worth it to test against any of the other ones? Let's have a look at our slides here just to double check. So there's a very high chance that it's a first order reaction, right? But let's just test. Let's just test for case number 4, right? Case 4, which is an nth order reaction. If you recall, for that case, the equation we had was Ca to the 1 minus n minus Ca naught to the 1 minus n is equal to n minus 1 kt. Okay. And we just need to basically verify the numbers in this case. So let's see. Let's see if we can get something here. So I'm going to test for case 4. First of all, I'm just going to set an n equals any arbitrary number, let's say 0.8. And I'm going to test case 4 by just writing the equation. So I have Ca, so in this case, Ca to the power 1 minus n, right, minus Ca naught, which is this number, to the power 1 minus n. So what am I really plotting here? Actually, that might not make sense, right? N minus 1 kt. So, okay, so if you want to test it for case number 4, you probably need to solve for our k. So let me go back to the whiteboard and then let's try to attempt solving for k. But basically, this is part B from this problem. So let me clear all drawings. Let me go here, and we're doing, which one is this, number 7? Part B, and I want to test versus nth order kinetics. So if you recall, for nth order, I have Ca 1 minus n minus Ca naught. 1 minus n is equal to n minus 1 kt. And what we could do in this case, we could just we just need to use the experimental data to find the best fit, right? And again, this is sort of an iterative type of approach. You wouldn't see this on the exam, but it's just for you to practice and start seeing things differently. Okay, so let's use first condition. So let's use not the first condition. Let's use second condition. So I'm gonna have Ca will be 500 into 1 minus n minus 1000 into 1 minus n is equal to n minus 1 k multiplied by t, which is 100. Can then use my other condition, or my third set of points, which is 333 1 minus n minus 1000 to 1 minus n is equal to n minus 1 k multiplied by t. In this case, it's 200. If I divide these two by each other, right, I'm gonna get 500, 1 minus n minus 1000, 1 minus n, divided by 333, 1 minus n minus 1000 to 1 minus n is equal to what? Is equal to half. And from here, we'll just have to iterate for n. So how about we take this expression back to Excel and try to iterate for n, see if we get something. So so back to Excel, let me show you how to iterate. Or actually, before iterating, let's rewrite this as a flat equality, right? So it will be 2 into 500, 1 minus n minus 1000 into 1 minus n is equal to 333, 1 minus n minus 1000, 1 minus n. If I move the 2 in, 2, 500, 1 minus n minus 2 plus 1. So I'm going to get minus 1000, 1 minus n minus 333, 1 minus n is equal to 0. And I'm basically solving this inequality. All right, so let's write this down. So here I'm going to set n is equal to a certain number, and then this expression has to be equal to 0. Let me move to Excel so that you see what I'm doing. So the expression I'm trying to do is let me go back to the whiteboard. Disappears when I stop sharing. Let me write this guy here. 2 into 500. Great. Okay, let's take this to Excel. So I'm gonna have 2 multiplied by 500 to the power 1 minus n, right? Minus 1000 to the power 1 minus n, minus 333 to the power 1 minus n, right? And I need this expression. I put 1 here, it's equals to 0. So it is a first order reaction, actually, at the end of the day. If I plug in 1, you get 0. Plug in any other number, you're gonna get some strange junk. Okay, so this was an obvious type of problem, but this is the logical way to approach these types of problems. Okay, let's move on from this problem. It's starting to get boring now. Let's save it. Let's clear all my drawings. Let's move on to the next one. Problem number 8. Okay, so in this problem, you're being told that at room temperature, sucrose is hydrolyzed by the catalytic action of the enzyme sucrase as follows. So you get sucrose, you got an enzyme sucrase, enzymes like a catalyst just breaks down the thing, and you get some products. And you're being told that starting with a sucrose concentration of Ca naught is equal to 1 millimole per liter, sorry, and an enzyme concentration Ca naught of 0.01 millimole per liter. The following kinetic data are obtained in a batch reactor. You're given some data. Determine whether these data can be reasonably fitted by a kinetic equation of the Michaelis-Menten type. Okay, so I have a rate expression here, and I want to verify that this data will fit this rate expression. And if it fits, find the constants K3 and Cm, and you're being told to solve it by the integral method. That's fine. So let's move on to the whiteboard first, and then we'll have to probably move on to Excel in a second. Okay, so in this problem, so let's write this problem number 8 right here. You're being told that, let me just recall, you're given some experimental data. You're given sucrose goes to products, and you have an enzyme. I'm gonna call it enzyme, because if I write sucrase, and then I won't be able to say it easily. And sucrose is denoted as A. So basically, I have Ca naught is equal to 1 milliliter per, or millimole per liter. Let me just erase this. Start to get sloppy now. Millimole per liter, and Ca naught is equal to 0.01 millimole per liter, right? And you're given a bunch of kinetic data, Ca versus time, and you're being asked determine if this fits this rate expression, which is minus Ra K3 Ca Ca naught divided by Ca plus Cm, where basically you have two constants in this case. K3 is a constant and Cm is a constant. You're being asked to solve for these two guys as well. So I need to check if the data fits this model. Okay. So what's the deal? How do you approach this? So let's see what we can do, right? Let's try to, because we're using an integral method. So let's rewrite this properly, right? So K3 CA CE naught divided by CA CM. I want to try to simplify this expression somehow, because plotting this guy is not as easy as it looks. So I want to simplify this so that I only have it as a function of CA, because I'm given data in terms of CA. So I want to really simplify this. So I'm going to start off by lumping my constants. And this is a typical approach. So step one in this approach would be lump your constants. So in this case, I have minus RA is equal to K3 CA naught, right? So I'm gonna lump these two guys together, multiplied by CA divided by CA plus CM, right? And so first step is lump constants, let's say, in the numerator, right? So I'm gonna do this first step, and usually the second step, so this is step number one. Step number two, and in this type of analysis, usually to remove constants from standing alone in denominator, right? And by that, I mean that this CM, I'm not happy with it. I want to have a 1 here. So to do this, I'm going to divide by CM. So I'm going to get K3 CA naught divided by CM multiplied. Oops, this guy going crazy now. CA. Okay. 1 second. Here we go. Multiplied by CA divided by 1 over CM CA plus 1. Okay, so I basically divided by CM, and now I'm going to define two constants. I'm going to say let K4 be equal to K3 CA naught divided by CM, and let K5 be equal to 1 over CM, right? So taking all of these expressions and going up here, so now I can rewrite my expression as minus RA is equal to K4 CA divided by K5 CA plus 1. And this is an easily integrated type of expression, right? Because let's see, if I say this is equal to minus dCA by dt, and we try to integrate this guy. So let's see how we're going to approach this. 1 second. Okay, sorry. So now we're back. Let's, so we're saying that in order to check this rate equation, I need to integrate. So I need to use the integral method. So what I did, first of all, lumped the constants in the numerator. Second step was that I removed any standalone constants in the denominator, and that means I'm just changing anything. So if I have CA plus A, I change it to CA plus 1, alpha CA plus 1 is the typical format. So in this case, I have K5 CA plus 1 is equal to minus dCA by dt. So now let's separate the variables and integrate. So I'm going to get, so if I cross multiply, I'm going to get K5 CA plus 1 divided by K4 CA multiplied by dCA, and this is equal to minus dt, right? If I expand this, so I'm gonna get K5 divided by K4 plus 1 over K4 CA, all of this dCA is equal to minus dt. And now if I integrate this from CA naught to CA, and I integrate this guy from 0 to t, I'm gonna get, let me save it, and okay, let me remember, what was it? So if I integrate, so I think what we had was, our expression was basically K4 CA divided by 1 plus K5 CA is equal to minus dCA by dt. We said we're gonna separate, like start integrating. So I get 1 minus K5 CA divided by K4 CA dCA is equal to dt, and this guy right here, makes sense? No, this has to be a plus, right? Yeah, so this guy right here will be equal to K5 divided by K4 plus 1 over K4 CA, all of this multiplied by D CA, and there's a minus sign here, is equal to minus dt. And we said I'm integrating this guy from CA naught to CA, and I'm integrating this guy from 0 to t. So basically, if I integrate the first expression, I'm gonna get K5 divided by K4 CA naught to CA, plus if I integrate this expression, I'm gonna get ln CA divided by K4 from CA naught to CA, and if I integrate this, I'm just going to get a t. Okay, let's go up here. Let's plug in the numbers. So I get basically K5 over K4 into CA minus CA naught plus ln CA divided by CA naught, right? Divided by K4 is equal to, actually this is minus t right here. Dropping this minus always. Okay, minus t. Sounds good. So now I have some sort of expression. So I want to be able to use this expression to verify the data, right? Use this verify the data somehow. And I want to be able to extract K5, K4. So ideally you want to have, you want unknowns to be the slope and intercept, right? Because if my unknowns are the slope and intercept, I just plot the data I have and I just read the slope, read the intercept, I get my unknowns. Otherwise, you're gonna start iterating and things like that. So how do I rearrange this to get these two as a slope and intercept? So first of all, let's try to linearize this. Let me multiply K4 across across this equation. So if I do this, I'm gonna get K5 into CA minus CA naught plus, right, ln CA divided by CA naught is equal to minus K4T. Okay, so now it's starting to take shape. Now let me try to use K5 as my intercept. So I'm going to divide by CA, CA naught. So in this case, I'm gonna get K5 plus ln CA divided by CA naught divided by CA minus CA naught is equal to minus K4 divided by CA minus CA naught multiplied by T. I want to get rid of this minus here. I can move it anywhere I want, but let's see. So if I plot this line, so in this case, if I plot this versus T, and the slope will be this, and the intercept will be this, right? So basically, let's rewrite this. So I'm gonna get K5 plus ln CA divided by CA naught divided by CA minus CA naught is equal to K4 over CA naught minus CA multiplied by T. So if I plot basically T versus ln CA over CA naught over CA minus CA naught, my intercept should be, or sorry, so if I plot it this way, my intercept here should be minus K5, right? And my slope should be equal to K4 divided by, no, then this doesn't make sense for it to be a slope. So actually what I need to plot is, I need to plot T over CA naught minus CA, right? So if I plot this expression right here, plot this expression, and versus this expression, this will be my slope, and this will be my intercept, right? Or basically minus intercept. Okay, let's try to implement this in Excel. So let me go to Excel. Actually, before going to Excel, let me rewrite this equation quickly and then copy it to Excel so that I remember it. So what I'm trying to plot basically will be ln CA over CA naught divided by CA minus CA naught is equal to T over CA naught minus CA multiplied by K4 minus K5, right? Okay, and this is the equation I want. Now let me move to Excel, and we'll take it from there. Okay, so let me jump to Excel here. Let me share Excel in this case. So this is the equation I'm trying to plot. So let's have a look at the data we're given. And so experimental data we're given, I have CA and I have T. And this is in millimole per liter. This is in hours. Why is my screen sharing first? There we go, resume share. All right, okay, here we go. And T is in hours. So let's have a look. So I got 0.84, 0.68. Good. So now I need to get ln CA naught, CA divided by CA naught divided by CA minus CA naught. So I'm getting basically ln CA divided by CA naught divided by CA minus CA naught, right? So let's calculate this is equal to ln CA divided by CA naught, which is F4, divided by CA minus CA naught right here. I'm just not happy with this. It's fine because the first point will give us a 0. It's okay. Okay, now let's write down the second guy. So T divided by CA naught minus CA. So in this case, it will be T divided by CA naught F4 minus CA. First point will be 0, it's fine. And now let's plot these two columns against each other and see. Hopefully we get a straight line. If we didn't get a straight line, then something is off, right? Yeah, so something does not make sense here. Let me double check the data we have. 0.84, 0.68, 53, 38, 27, 16, 09, 04, 00, 040, 18, 006, 0025. Then just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me verify this equation. So I have ln of ln of what? Oh, it's right here. So ln of CA divided by CA naught minus CA minus CA naught, right? Is equal to K4 multiplied by T divided by CA naught, right, is equal to K4, so is equal to T divided by CA naught minus CA. Yeah, it looks fine. Let's go back to the whiteboard, see that, just have a second look at our calculations. We didn't drop a minus sign anywhere. So we integrated this guy, so we got from CA naught to CA plus ln CA divided by CA naught is equal to minus K4T, right? CA CA minus CA naught ln CA minus CA naught K4 minus T, CA minus CA naught plus ln CA divided by CA naught is equal to minus K4 T, so I just multiplied the K4. I divided by this guy, so I get K5 plus ln CA divided by CA naught minus CA naught is equal to minus K4 divided by CA minus CA naught, right? And I just multiplied this minus by the denominator, so I got CA naught minus CA T, and then I moved the K5 to the other side. So it looks fine. Ln CA divided by CA naught over CA minus CA naught is equal to T over CA naught minus CA, right? T over CA naught minus CA multiplied by K4 minus K5. Okay, so it seems fine to me from a derivation side. Let's go back and verify what we did here. Do something off. Okay, let's have a look. Let me just verify these numbers here. Oh, yes. I think what we did wrong was that CA note was given. So CA note is given in the problem to be 1, right? 1 millimole per liter. Okay, that makes sense. Because I used this number as CA note and forgot that we were given a CA note. So let me move the CA note to here. Actually, it's wrong. So in this case, yeah, let me use the second one and move the CA note to 1. And in this case, I'm going to move the CA note to 1 as well. And we're going to drag them in directions. Hopefully this straightens out the line, right? Okay, here we go. So now the line looks somewhat straight, and I think even this point will work. Yeah, so the data looks reasonably okayish now. Okay, so now let's add a trend line and find the slope and the intercept of this line using Excel. You can find the slope and intercept by hand. You know, feel free to do whatever makes you happy. So your slope in this case is 0.9879 and your intercept is 5.0497. Okay, so now let's go back and evaluate the two constants we were looking for from this problem. Okay, let me go back to the whiteboard. Okay, so we were able to find the slope. The slope in this case, let me change the line to red. So we found the slope in this case, we found K4. Let me save, and then let me erase this chunk right here so I can do some work. Sorry. So we found out the slope to be 0.9879, and our intercept in this case was 5.0497. Was it 5 or was it minus 5? It was 5. Okay. So that's fine. 9.8. That's fine. Okay, so now let's so from the previous slide or from the previous whiteboard, if you recall, we said that. Let me find it. I don't remember. It was K4. Said that K4 is K3 CE0 divided by CM, right? So K4 will be CE0 divided by CM, and K5 will be where's this thing at? Here it is. K5 is 1 over CM, and K5 will be 1 over CM, right? Let me just double check the Excel one last time, just make sure we don't have any strange sign thing happening. CA minus CA note, okay, good. And CA over CA note, and then T divided by CA note minus CA. So in our case, so K5 will actually be what? It's minus K5. And I'm assuming K5 will be minus, right? That makes sense. So this implies that Cm will be basically 1 over 5. In this case, 1 divided by 5.0497 is 0.198 or minus 0.198 millimole per liter. Then I'm going to plug this guy here, and we're given that CE0 is what? We're given that CE0 is 0.01. So I need to find K3, right? And this is equal to 0.9879. This guy is given to be 0.01. This guy right here is minus 0.198. So this implies that K3 is equal to what? Multiplied by 0.9879. Will be equal to minus 19.5, right? Minus 19.5, and the units for this guy will be hour minus 1, right? Because this will be hour divided by mole meter cubed, so this will be mole right? So this, because this is 1 over mole meter cubed, so this will be 1 over mole meter cubed. So Cm will be, sorry, liter, or wait, let's verify these units. So this Ca is millimole per liter, which means that K4 is in hour minus 1, and K5 is in 1 over millimole per liter, which means that Cm is just in millimole per liter. And because K4 is in hour minus 1, this is in millimole per liter, this is millimole per liter, you cancel out. So K3 is in hour minus 1, okay? So the final answer for this problem will be that, yes, our kinetics are verified, and the two values for the constants, let me save this, and let's just do one last slide here, where we solve this problem, or when we just write the solution. So we say minus R3, or sorry, minus RA is equal to K3 CA CA0 divided by CA plus CM, where CM has a value of, we said was, what was it? Let me recall it right here. Yeah, CM was minus 0.198, sorry, minus 0.198, and K3 is 19.56, right? And we said this is millimole per liter, and this is hour minus 1. And yes, yes, it fits the data, right? In Excel. Okay, so let's revise this problem and just reiterate what we did. So in this problem, you're given one second. In this problem, you're given a reaction, you're given CA note, you're given CE note, you're given a bunch of experimental data, and you're asked to verify whether this model or this kinetic model fits this experimental data, right? And in order to do so, and you're being asked to use the integral method to do so, and then once you verify it fits, just double check K3 and or find the values for K3 and find the values for M, right? Sounds good. So let's go back to the starting point here. Let me see if I can share these whiteboards, which we developed. Just waiting for it to load. Okay. So we started off by just listing a given, and in order to be able to verify whether your experimental data of CA versus T fits this model using the integral method, we need to sort of reverse engineer this kinetic method. And usually the steps is step one is to lump all the constants in your numerator. And this is what we did. We lumped K3 and CE0. And then the second step is to usually remove any standalone constants from the denominator. And in this case, Cm, which is this guy right here, and we remove this by dividing by Cm. So I have two constants in this case. The first constant is K3CE0 divided by Cm, which is lumping these three constants. And then the second one is 1 over Cm Ca plus 1. So plus 1 is better than having plus a standalone constant, because usually easier to deal with plus 1 numerically and other types of things. So what I did at this point, I renamed these three constants together as K4, K4CE0 divided by Cm, and I renamed 1 over Cm to be K5. And we wrote the expression as K4Ca divided by K5Ca plus 1 is equal to minus dCa by dt. And then basically we had to integrate because we're using the integral method. So I separated the variables. I put all the CAs on one side with dCa and the dTs on the other side. And once we got to this point, let me open the second whiteboard here. And once we got to this point, basically integrated from CA0 to CA, I just did some algebra. First of all, I separated this fraction into two smaller fractions and then integrated, and you got the integral. So K5 over K4 Ca to Ca0 plus ln Ca over K4 Ca to Ca0 is equal to minus T, right? I plugged in my limits, so I get K5 over K4 Ca minus Ca0 plus ln Ca divided by Ca0 over K4 is equal to minus T, right? Okay, so I have K5 over K4 Ca minus Ca naught plus ln Ca divided by Ca naught over K4 is equal to minus T. And ideally, in order to get these unknowns, I want them to be my slope and my intercept, so that when I plot my line, I can just read off the slope, read off the intercept, get these constants. So we did some rearranging here. So I multiplied, first of all, by K4 across, and get K5 Ca minus Ca naught plus ln Ca over Ca naught is equal to minus K4 T. And then I basically divided by Ca over Ca naught. So I got K5 plus ln Ca over Ca naught divided by Ca minus Ca naught is equal to minus K4 over Ca minus Ca naught multiplied by T. I removed this minus sign by moving it down there. So I got K5 plus ln Ca over Ca naught divided by Ca minus Ca naught is equal to K4 multiplied by T over Ca naught minus Ca. And I plotted basically this expression versus this expression using this equation right here. So this was the refined equation. We plotted this as the y, this as the x variable. This will be the slope, and this will be the intercept. And this is what we did in our Excel sheet here. Right, and basically in our Excel sheet, we got ln Ca naught, Ca divided by Ca naught divided by Ca minus Ca naught. Let's make this a capital letter. And then T Ca naught minus Ca, plotted these two guys versus each other, got the slope and the intercept, and then we got the rest of the variables. Okay, so that's it for this problem. Let's go back to the homework and see if we have any other problems left. Let's wrap this up right here. Okay, problem number 9. For the decomposition, let me clean up. Okay, so in this problem, you're being told for the decomposition A goes to R, Ca0 is equal to 1 mole per liter, and a batch reactor conversion is 75% after 1 hour and is just complete after 2 hours. Find the rate equation to represent these kinetics. Okay, let me go to the whiteboard here. And let me, actually this has to be a minus as well. Just be careful of these signs. Let me save this guy. Let me clear all my drawings. And let's do problem number 9, right? So in this problem, what do we have? For the decomposition, A goes to R. So you're being told that A goes to R. You're being told that Ca naught is equal to 1 mole per liter. And in a batch reactor, the conversion is equal to 0.75 when time is equal to 1 hour. So let's call this XA1 and T1. You're also being told that just complete after 2 hours. So XA2 is equal to 1, basically complete. When T2 is equal to 2 hours, you're being told to find a rate equation. So you need to basically find minus RA and basically find N, right? So you need to find the order and find the rate equation. Okay, so in order to find N, first of all, we need to determine the, or use case number 4, right? So if you recall, case number 4 for an nth order reaction. So in order to get N, case number 4, if we remember, it's Ca 1 minus N, minus Ca naught 1 minus N is equal to N minus 1 KT. And if I'm going to rewrite it in terms of conversion, so if you remember, XA is equal to 1 minus Ca over Ca naught, which means that Ca is equal to Ca naught into 1 minus XA. If I plug these guys into each other, I'm going to get Ca naught into 1 minus N into 1 minus XA, 1 minus N minus 1 is equal to N minus 1 KT, right? So this is the equation we have. So now let's use this expression as our performance equation and plug in the numbers we were given. Okay, so let's try to do this. So in this case, let's write them for both conditions. This guy, there we go. So I have Ca naught is 1, right? So 1 into 1 minus N into 1 minus XA is 0.75 into 1 minus N minus 1 is equal to N minus 1 N minus 1 into, where's the K? K, and T in this case is 1 hour. So this is the first set of conditions. We can clean this up probably. Let's do this before moving on. So I'm gonna get 0.25 into 1 minus N minus 1 is equal to N minus 1 K, right? So it's using the first set of conditions. Now let's use the second set of conditions. So in this case, what do we have? I have XA is 1 and T is 2 hours. Okay, and CA0 is also 1. 1 minus N, 1 minus 1, 1 minus N, minus 1 is equal to N minus 1 K into 2. And this is basically 0. So this is 1, right? This is 0, and I get minus 1. So I have minus 1 is equal to N minus 1 K into 2. So I have two equations, two unknowns. Let's try and so let's divide them first of all. Let's divide this equation. I'll call it I. I'm dividing it by I. So I get what? 0.25 1 minus N minus 1 divided by minus 1 is equal to N minus 1 K over N minus 1 K into 2. I can cancel these by assuming N is not equal to 1, of course. If N is equal to 1, then we need to go back to this step, right? Can't just jump back to the step. And of course, these little k's cancel. So I get basically 0.25 1 minus N is equal to, I'm going to move this minus 1 here. I get minus half plus 1 is equal to 0.5. So what's the answer here? So N has to be, what, half, right? It's quite obvious that N is half. But, you know, if you really want to, you can take ln of both sides. Ln of 0.25, 1 minus N is equal to ln 0.5, so 1 minus N is equal to ln 0.25 divided by ln 0.5. And does this make sense? No, it's ln 0.5 minus ln 0.25. I mean, the answer is 2, but, you know, it's just going slowly through the math. Hopefully you don't need this part, but, you know, it's always good to remember these little math things. Ln 0.5 divided by ln 0.25 is 2, right? Is it 2 or is it half? It's half, sorry. So I have 1 minus N is equal to half, which means that N is equal to half. Okay? So this means that, you know, your N is half. So now let's go back to original question, which is asking to find the rate expression right here. So minus RA is equal to minus dCA by dt, and this is equal to K CA to the power N. So we need to get K, right? So we have N is equal to half. Let's go, I think we have an easy equation here which we can get K from. So let's use this guy to get K. So if I have N to be equal to 0.5, this means that minus 1, so I'm using equation number 2 to get K. Minus 1 is equal to half minus 1 is minus half, right? Multiplied by 2 multiplied by K. So this means that K is equal to 1, and the units of K will be what? Any ideas? Because it's a half order reaction, it will be mole to the half divided by liter to the half multiplied by hour, right? Just go to the first lecture and remember how to get the units for these constants, right? So this, my rate expression will be 1 mole liter to the half hour multiplied by CA to the 0.5. Okay, very simple problem. Okay, so this is the end of homework number 2. There's different ways of thinking about things, different ways of approaching things. Try them. Struggling, come to office hours. We'll deal with it. But just give yourself a chance to absorb these different ways of solving these problems. All right. Thank you very much.